Hello, and welcome to the Rittmeyer Penstock Leak Detection System webinar, or as we call it, PLDS. My name is Steve Hendren, and I'm the head of the Rittmeyer North American team, and I'll be your presenter today. Thank you for coming. We'll begin with a brief introduction to Rittmeyer for those who don't know us, just to give you some background, a little context so you know where we're coming from. Then we'll go into some example cases, followed by an overview and then some details of the PLDS or Penstock Leak Detection System, and then some other considerations you need to take into account when employing such a system. Rittmeyer is a Swiss company. We've been around for 116 years and have been a member of the Brugg Group for probably 40 years now. We've been in the instrument market the entire time, making instruments for measuring water around such applications as hydropower, irrigation, water supply, and wastewater systems. We were one of the originals to come out with flow meters, the transit time flow meters as specified in the ASME and IEC turbine performance test specs. And as near as I can piece together, there were 3 of us to start with. There are 2 of us left of the original players in this that have the real experience in this market. And Rittmeyer is the world leader by far in this market. We've recently opened our new, in addition to our headquarters in Switzerland, we've recently opened a regional headquarters in North America in Algodones, New Mexico. And we have our Asian regional headquarters in Singapore. We're also supported by 5 European subsidiaries and then many global partners around the world. Rittmeyer's product line is made up of smart instruments in the area of flow, position, and level measurement. Our main flow product is the Rysonic Modular, which is a transit time flow meter that meets the different turbine performance test specs, can measure very large pipes and channels, as well as down to very small pipes with our clamp-on solution. And of course, we address the markets that we just discussed. Our smart instruments run smart applications resident on them. Smart apps, as I call them, for the flow meter include the Penstock leak detection system that we're here to talk about today, and also includes silt monitoring. If you have aggressive silt that is eroding your runners or other components in your system, then let us know, and we should talk about silt monitoring some more. We can also measure real-time efficiency monitoring and a few other smart apps. Our position products include our repos and revert product lines. They are all optical encoders, and more than anything, they are super rugged. They're meant for the temperature extremes, for the tough environment it can be in. They have a ton of lightning protection, and they're really the only products purpose-built for dams, as well as for things like drawbridges and valves. The difference between our repos and revert is the repos is a shaft input, so you would couple it to some sort of rotating shaft. The revert has a built-in pendulum, so for a tainter gate or a radial gate of any sort, a crest gate, or a valve or a drawbridge, you can just bolt the revert to the gate and it will give you the angle reading directly. The difference between our standard product and our smart versions is the smart versions have our instrument controller built into them, and they can run smart apps. Smart apps for our position products include things like measuring gate flow, gate skew. If you have a long gate and you want to make sure it's not twisting, we can measure both the position and that twist, as well as other interesting applications like overspeed and underspeed and that sort of business. Our level products are built around our Rypress pressure transducers. They come in various forms. When we couple that with our instrument controller, it becomes our Rypress Smart and is able to run smart applications. And our Rypress Premium is for precision applications where you need extreme accuracy without the need to recalibrate over the life of the product. Smart apps for our level products can be run on either the Rypress Smart or the Rypress Premium, and they include redundant level sensors for critical applications, and we can measure flow through weirs and venturis and other constrictions, as well as gates. And we have a Winter Kennedy flow meter application that can measure the flow on up to 4 units at the same time on one Rypress Smart product. Notice that we can do flow a number of different ways, with, of course, our Rysonic Modular being our flagship product. When we look at the leak detection market, what we see are two broad classes of leak detection. There's rupture detections that have been around for quite a while. And then over the last 25 years, Rittmeyer has built up a penstock leak detection product line and have sold over 300 of these in the last 25 years. We've seen a few other products similar to our PLDS that have been put together mostly by end customers or engineering firms. And as near as we can tell, nobody has ever done more than just a few of them. And as near as we can tell, nobody has had very good success with this. We work with a global engineering firm that has worked with a couple of these in South America, and they just didn't see very good success with them, and they will now only recommend Rittmeyer's PLDS. I have a customer in the Pacific Northwest of the United States that I met with in the last couple of months. Turns out they had put one in about 10 years ago of their own design and never got it working good enough to even bother to turn on and implement. And now we're talking about putting ours in there instead. As near as we can tell, no other flow meter manufacturer has done even one of these. We do know that some of their equipment has been used by others in a penstock leak detection design, but as near as we can tell, they didn't participate in that design. Now that's the way we see it. If you guys know of any systems out there that are working good, then please let us know. We'd love to see those and have a nice conversation with whoever has that. If you want to work with somebody else, an engineering firm or another manufacturer on a penstock leak detection system, I recommend you ask them for a reference list and dig into that reference list to make sure that you like what you see there. And we're happy to provide the same. Of course, you can make your own leak detection system, and if you wanted to do that, you would probably start with 2 flow meters, either Rittmeyer's or somebody else's. You would need some sort of a controller to do all the calculations and make all the decisions and take the actions, and you would need a comm link to tie them all together. The Rittmeyer system is similar, only it uses smart instruments, so we just have 2 flow meters and the comm link tying them together. There's no need for a PLC or any intermediary in between. All of that work is done within the smart flow meters themselves. In both cases, you need to buy flow meters, you need to install and commission those flow meters, and you need to do the special commissioning and tune-up associated with the penstock leak detection application. If you want to do your own, of course, you have to take on the hardware and software development yourself, and you have to learn the additional details of doing the PLDS tune-up. With the Rittmeyer system, you buy the 2 flow meters, and it only takes 2 extra days for commissioning, so it costs virtually the same as 2 flow meters themselves, and it alleviates the extra time as well as risk of making your own system. To set the groundwork for the rest of the conversation, it's worth reviewing some of these risks. We all know them, but let's bring them to top of mind. Of course, if you live in an earthquake zone, we all know what the risks are with penstocks and earthquakes. Landslides can happen in many areas where there are penstocks, especially long penstocks, because chances are you're coming down a mountainside to build up head, and that's half the reason of having the penstock. And then, of course, any of us can experience water hammers. These others are a little more specific, but things that we have seen. Your risks can change with your penstock as well. A couple of examples come to mind. I have a customer in Utah who's had a penstock coming down a mountainside for the last 80 or more years, and it then runs under a kilometer or 2 of level ground, and it's buried at that point. 40 or so years ago, the city planners allowed houses to be built right up to that penstock. The electric company warned them, asked them not to allow that and to put an easement in, and the city planners chose otherwise. So now the houses are built within 6 feet or about 2 meters of this penstock. If something happens, the utility doesn't get to say, well, we warned you. Instead, this is now their risk that they've assumed. So they didn't do anything different, but their risk changed. I have another customer who has a penstock about 2 kilometers long that is coming down a hillside, and we'll visit this one again later. And For 50 or so years, it's been fine. Then in the last 10 or 20 years, that hillside has started to become unstable, and they're very concerned about a landslide and rock slides taking out their penstock there. So again, risks can change. Fortunately, penstock ruptures and disasters are rare, but they do happen. And here are just a couple of examples. In 1984 in the USA, this plant experienced a water hammer, and you see did quite a bit of damage. There were 5 people working inside the powerhouse at the time. They were swept out through a hole that had just been torn through the other side by the surge, carried downstream, and unfortunately 4 of them did not survive. This one in Switzerland happened 20 years ago, and it's in a deep tunnel under very high pressure. The water forced its way up through the rock, created a geyser up in this area, and of course this huge inundation zone, as you can see. To give you a sense of scale, from somewhere up here down to the Rhine River down here is about 800 meters. So this is a very large inundation zone. And it took them over 10 years to get the plant back online, and of course 3 people were killed in this. Fortunately, this is not a very populated area. 5 years ago in India, this rupture happened, tore through the steel and concrete encasement. This had been leaking for a while, and some passerbys had notified them about this. Now, that's not necessarily good news, but the good news we can take away from this is that fine leak detection can work. It can give us enough notification to prevent a full-on rupture. You know, if there's an earthquake or a landslide, well, then all bets are off. There will be no warning. But if it's a weld breaking or some other defect in the penstock, as was seen here, there is hope. A leak detection system with enough granularity can help you prevent these things. And then just recently, 6 months ago, as of this recording, this one happened in India. This, you can see quite a geyser. Fair amount ahead. This is a concrete tunnel, and actually this was from acid in the rivers, had been from mining problems, had been eating away at their penstock, and they knew about it and just weren't able to get to this section in time. So what can we do about these sorts of things? You know, some of it is maintenance related, some is other safety practice related, but sometimes they just happen. In those cases, really early detection and rapid response is the only hope we have to mitigate this. Often people only look at above ground penstocks when they think about leak detection. You think if it's buried or in a tunnel, you've got the counter pressure of the ground around it that's going to help at least minimize any damage of a rupture. And there's certainly some truth to that. But if you look at these 4 examples in particular, they were all buried tunnels. The one in Switzerland was actually 100 meters deep and worked its way up through fissures in the rock and through that very thick steel pipe and made a geyser in that large inundation zone, as you see. So while perhaps safer, even underground penstocks and tunnels need to be considered when looking at your safety plan. So looking at solutions, rupture detection is one that's been around for quite a while. It usually consists of a velocity sensor of some sort, a pitot tube or a pendulum or a similar sort of device. And they measure the velocity just usually at the edge of the penstock. So if it's a very large penstock, it may represent the overall flow well, or it may not. I worked with a customer recently who has a 5 or 6 meter tunnel and a pitot tube right at the edge, and it goes into a header of 4 or 6 penstocks. And what they're seeing is that depending on how that header is loaded, if it's just one of the end units it's on, or there's 2 or 3 versus all of them, that this velocity sensor may have different readings even if the flow hasn't changed. And so it's led to some nuisance trips in their case, and they've had to set the velocity, the trip level high enough that it's questionable whether it's really doing any good or not. Now, in other cases, they work actually quite well, but they can be a nuisance from time to time, so keep that in mind. Another solution is a pressure switch, where if the rupture is an overvelocity, it can draw the forebay down low enough that it starts to draw air into the penstock, then the pressure switch will trip whenever the air gets sucked in. This is application specific because that won't happen in many architectures. But in cases where it does, this is an option, and we've actually employed it in some of ours for various reasons, which I could go into on a private conversation. But it can work quite well. It can have some problems of its own, but it also can work quite well, and it's very application specific. In all cases, an overspeed sensor is only going to detect a rupture if it exceeds the maximum flow that you're ever expecting for that system. If you have a large penstock, then you could still, even if it's only a rupture of 80% of the flow, it could still be quite catastrophic, and an overspeed sensor will never see it. So they're inexpensive, they're cheap and cheerful, they are better than nothing, but they're of limited utility. What Rittmeyer has developed is a full penstock leak detection system. And for us that means 2 flow meters, one at the upper section and one at the lower section. With that, we can detect 3 levels of penstock leaks. We have a full rupture detection that acts very quickly. We have our gross leak detection. This is what we've seen other people do. It's the simple A minus B, subtract the 2 flows and get this differential flow, or as we call it, DQ. And then we have our exclusive fine leak detection that gets down to very small leaks. Looking at this in a little more detail, the rupture detection can act quite fast. Ours is a full flow meter, so it isn't going to get fooled by unequal flow distributions like a pitot tube could. It's going to respond very fast, and there are cases where you'll want it to actually do an autonomous gate closure. It can be a single-ended device, much like it would be with an overspeed. And we have some advanced functions we can put in to fine-tune a rupture plus detection, if you will, specific to your site. Gross leak detection is what we've seen other people do. This is that simple A minus B function. We can get down to about a 4 to 7% leak detection range with our PLDS. Reports we've gotten from others is that reaching 10 or 15% can be challenging, and we've kind of solved that problem and gotten much better results. Our fine leak detection uses our exclusive integration algorithm. If it's a small leak, it can take a while to respond. So that's the trade-off we make with that. But hopefully it can detect a fine enough leak, and we often get to a 1% range where you might have, as in the case in India, where we could detect that before it becomes a rupture. So you stand a real chance of that with our fine leak detection system. If we look at the basic PLDS architecture for the Rittmeyer PLDS, which of course is based on the Risonic modular flow meters, these flow meters are smart flow meters. So our system just requires the 2 flow meters and the communications link between them. The one can talk directly to the other because they have the math functions and the advanced communications and the I/O necessary to perform all the functions of the PLDS. These flow meters can monitor more than 1 penstock. A pair of flow meters can monitor up to 4 penstocks. It is a safety system, so we tend to limit that to 2 penstocks as a good trade-off between cost and the ability of a single point failure taking out too much of your protection system. Our flow meters have built-in web servers. So to communicate with them, to set them up or do preventative maintenance, you just need a device with an Ethernet port and a web browser, be it a tablet, a PC, or some other device. There's no special software to install, to become obsolete, to lose. It's future-proof in that regard. Because we're working on an Ethernet system, we can tie into both flow meters from a single point. In fact, if your Ethernet switch here is also connected to the instrument area network that goes into your control room, you can sit in your control room and look at both flow meters. So there's no running back and forth between the head gates and the powerhouse to adjust these or interrogate these meters. And finally, everything is menu driven. There is no special programming for this. To set up the COM link, one flow meter will set up a remote input from the one flow meter to the other by going to the menu and entering the IP address of the other flow meter and which register we want to read, the one that contains the flow. And now it will continually update the flow so that the one flow meter has flow for both flow meters as if they were both resident. If we want to do the math functions of the gross leak detection, that's a simple A minus B. We'd go into the section for defining a new function, and we would, from a pick list, select subtraction, so we can do the subtraction function. We go to the next next menus to define the inputs. Again, from a pick list, we'd pick the flow from the local meter and then that remote flow that we've just set up. We hit save, and it's really that simple. It gives us a ton of flexibility, and it's so simple that we don't have to pre-program them. We can come to site and configure them right on site in a matter of hours, and no extra work in that regard. So that all seems easy, right? Then why is it that people struggle with putting PLDSs together? Well, I think the first thing is experience. It matters. It's hard to do this just once. And if you aren't very familiar with flow meters, you don't know some of the nuances that are going to get you when you're trying to get to a decent leak detection level. Where you site the flow meter transducers, that section of pipe is called the measurement section. Where that measurement section is sited matters, and we'll look at the details of that. And finally, there are some tricky penstock architectures that can come into play that can throw curveballs at us. That, of course, Rittmeyer has addressed. And there are a few other considerations I want to bring up if you want to embark on such a project. So taking them one by one, the transducer siting, again, matters here. Per the standards, you need a straight section of pipe to install the transducers, to put that measurement section in. You typically want 8 to 10 diameters of straight pipe upstream and 3 to 5 down. So if we look at a real world example of this, we might want to put the flow meters in these sections because this is a generate only penstock structure. And so this is a nice straight section, and down here is another nice straight section. So those would be good from a flow meter only consideration. The problem is we can only protect what's between the two measurement sections. Everything else remains unprotected, and that's just, in this case, way too much. So we want to push those flow meter sections as far to each end as possible. So then we can get the full coverage. The problem being those aren't necessarily good measurement sections. So what are the effects of these poor measurement locations? Well, I've assembled some data, fictitious data that I put into a spreadsheet just to illustrate this point. If the black line here is the actual flow, you can see that flow meters in a poor measurement section can face uneven flow distributions, which will vary as the flow rate varies. And so this brown line is similar to some of the things we've seen at a flow meter, for instance, near an intake. And the distortions can be quite big and the errors can be quite large. And again, they vary with flow rate. Sometimes the other flow meter is in a better measurement location, and so I've just illustrated that with the gray line. The difference between those is this DQ, and that's the gross leak detection. And in this example, though rather extreme, it shows that in this case, the residual errors are on that 16% or so range, and so it means you can't detect leaks that are any lower than that. But if these are repeatable, then it can be corrected. Rittmeyer has a very specialized linearization function that does a curve fitting to try and match those curves well, and we can compensate for this almost perfectly, much better than a simple lookup table that we've seen other people do in the field. So this is one of the things that really sets Rittmeyer's PLDS apart from anything else that we've seen out there, and makes ours perform considerably better. Now, if the flow meters can be put into a less than ideal measurement section, does that mean we could also use lower cost flow meters? And again, if it's repeatable, then we might not need the best flow meters. So we have a number of locations where we've just done 2 paths at both ends. And we even do clamp-ons. I have one in the works right now that'll be installed here in the next few months. That's just clamp-on flow meters. Other cases, we might want to have a good flow meter for turbine performance testing, and then for a small incremental cost, you can turn that into a PLDS. We always recommend at least a minimum of 2 paths because it is a safety system and you want the redundancy. Our system recovers very well from a failed path. It will look at all the remaining paths and try to decide what that path, infer what that path might be reading. And so you often will see either no change or very minimal change when a path fails. So this is a very good way to address that safety aspect of it. There are cases where we'll need to increase the number of paths to deal with poor hydraulic conditions. So we can't always get away with 2 paths, but very often we can. Now let's look at some of the unique penstock architectures that we come across, starting with bifurcations. In this example, we have a penstock coming down a hill, which then goes into the powerhouse and bifurcates to 2 units. We have a choice of where to put the lower flow meter in this case. We could do the flow meter before the bifurcation, and this is actually a better measurement section, so there's some real advantages to doing so. However, in this case, since it's buried to the powerhouse, we would have to use internally mounted transducers. There's no problem with that. They are a little more expensive. The serviceability is a little more difficult. But again, this is a better measurement location, and you have to make the trade-offs for that particular site. If you are going to do internally mounted transducers, then I encourage you to check out Rittmeyer's unique cable protection system. You have to protect the coax cables inside the penstock until you're able to pull them out. And Rittmeyer has a very unique solution that you should check out before you make any decisions on internally mounted transducers. Turning back to this bifurcation example, if we choose to do penetrating transducers after the bifurcation, then we simply have to sum those 2 flows together to get the lower flow meter, and it works into the equation just like that. However, there are some interesting challenges that come up. If it's calibrated with both units running, then what happens if only one unit is running? Does the flow distribution profile through this flow meter change? And it can. And if so, what effect does that have on the flow reading and on the balancing of the whole PLDS system? Similarly, you have load rejects. Now you have dynamic situations thrown in there for a time until things stabilize out. And so Rittmeyer has some advanced parameters that we can adjust to get the best balance for this and really make this work the best. The next interesting challenge comes with pump storage systems. If you look at this example, and it's typical of many of them, you'll see that they're in generate mode, the upper flow meter is located close to an intake, and it's going to see a lot of flow distortions, again, that vary over the flow rates. The lower flow meter is in a good or at least better measurement location, and in generate mode will often give decent results. However, when you turn around to pump mode, now this lower flow meter is in a very poor location near a pump, whereas this upper flow meter, at least in this example, is in an excellent location. So if you calibrate for, say, the generate mode, the pump mode can now be quite a bit off, even worse than if you hadn't calibrated it sometimes. So getting these 2 modes to balance out can be a real trick. Rittmeyer has some advanced algorithms that address this squarely, and we can compensate for it almost perfectly. And the final penstock architecture I want to address is one that includes surge tanks in the middle. So if you look at this example, in steady state, this is just a simple PLDS. The level in the surge tank remains constant, and what goes in must come out. That changes during any sort of a transient condition, changes in flows or anything else that causes the level in the surge tank to change. Now we have to keep track of that water because it can look like, if the surge tank is filling, it can look like there's missing flow when you compare the Q1 and Q2. So you have to account for that volume. That's a volume, whereas the others are flow, so you have to do the additional math to convert that to a flow in the surge tank so that you can do the math correctly. Again, this is a challenge we have faced a number of times. If you have this situation, let us know and we'll put a proposal together for you. When deploying a PLDS system, we urge you to keep that system autonomous. Now, what do I mean by that? I mean, don't mix it with your standard plant PLCs, balance of plant PLCs, or any other existing systems. Why is that? Well, if you look at this, it looks just like a target. Think about some of those early examples where the powerhouse was either partially or fully destroyed from a rupture. By keeping the system separate, then you stand a chance of taking that smaller system and hardening it, isolating it so that it at least can survive for a few minutes to get the job done and get that upper gate closed. The Rittmeyer system is fully autonomous, and so that's been taken care of for you. Now, an autonomous system is different than autonomous gate closures. An autonomous gate closure means that the gate will close even when the plant PLC is not in commission or not able to talk to the gate. Normally, you want to be very careful with this because if you have a false trip or even a real trip and you close this gate while there's still flow, you can collapse the penstock, or you can dry up the bearings and you can cause a lot of damage. So more than just having to repair a penstock, you now have a lot of work to do. So whenever possible, you want the plant PLC to lead the shutdown in a nice, organized manner. But when you get to, here's an example where we're looking at an autonomous gate closure. In this case, it's about a 2-kilometer penstock. But to get there by truck, it's a good 25 minutes or more drive. So you don't have time to go inspect something and find out why there's an alarm or what's happening if there's a loss of communication. In this location, they don't have good comlink alternatives. So what they're having to do is put in a radio link with a repeater. That repeater is unfortunately having to be mounted fairly close to the penstock. This is that site where I said over the last 10 or 20 years, this hillside has gotten to be unstable. So they're very concerned about a rock slide taking out this above ground penstock. That radio repeater is going to have to be in the vicinity of that. So it is certainly possible that the same rock slide that takes out the penstock could take out that repeater tower. Now these guys are smart. They're just, and they know better than to do that. They're just stuck and they don't have any other good alternatives. So they're going to isolate them as much as possible. But in addition to that, we're going to put in a special case where there can be an autonomous gate closure. Now the basic logic is going to look like that. If you look at these last 3 to start with, under most conditions, the plant PLC is going to organize the shutdown. The PLDS is going to alert the PLC to do that, but the plant PLC is going to organize the shutdown. In the case where there is a rupture alarm and the comlink has been lost, now the plant's going to shut down, the plant PLC will shut down the units, but also the gate will continue to listen for that communication to come back, and if after several minutes it does not, it's going to start an autonomous gate closure. It's going to assume that the reason that it hasn't heard from the plant PLC and it's seeing a rupture condition, it's going to assume that that relay has been, that repeater tower has been washed away as well and start a shutdown. So there are definitely cases where we want there to be an autonomous gate closure as an option, but we want to limit the conditions where that can happen. The next concept I'd like to introduce you to has to do with integrating PLDS with your penstock lifecycle management strategy. In a basic strategy, if we ignore the yellow for just a moment, you have the option to maintain your existing penstock, to do a refurbishment, or to replace it. And of course, the risk and associated costs are inversely proportional in each of these scenarios. If you look at adding PLDS to any of these strategies, the incremental cost is very small, yet there's a real impact on the risk profile. We talk about not wanting to end up in the newspaper. My corollary to that is if you're going to end up in the newspaper, you better have a good story to tell. If you've done either worked with an existing penstock or done a refurbishment and there's a problem, the public outcry, of course, is going to be, why didn't you do more? Why didn't you do that next step? Well, you've done the analysis, you did the smart things, but if you also have integrated a PLDS, your story becomes, Well, we made this good analysis, but then we also added this safety system, and because of that, we were able to shut off the leak this much faster, avoiding this much damage, and so on. This becomes a much better story to tell. It addresses your real responsibility, and it addresses that PR challenge as well. So most of our customers look at this as cheap insurance on their penstock management. The final thought I want to leave you with is Rittmeyer makes smart instruments, and we can run a number of smart apps. So if you employ a PLDS, you can also employ one of our other smart apps. So if you have a PLDS on a mountain site in an area where there's a lot of very abrasive glacial runoff in the spring, we can add silt monitoring. There's no additional hardware. It's just another half day of commissioning to get the silt monitoring set up. So we can run multiple smart apps in our flow meters. So that is worth considering as well. Or in just a standard flow meter, it's worth considering some of these other smart apps. So I thank you for your time. We welcome any sort of conversation with you, even if you're just thinking about it. The earlier we start talking, the better. And so give us a call. These are our contacts worldwide, and we're happy to get involved even at the conversation stage so you can plan accordingly. Thank you for your time. We have more webinars coming in the future, so keep an eye out for our cable protection, CFD, and some other webinars to come. Thank you for spending this time with me on the penstock leak detection system, and we look forward to working with you in the future.